Hello dear learner, I, Mr. Sri Krishna Baukan from Delonic Society's Baramati College of Pharmacy, Baranpur, Baramati. Here I would like to welcome all of you for today's session which is entitled as Oxidation Reduction Type of Titration. Particularly here I am going to explain iodine type of titrations. After completion of this video, the learner will able to differentiate iodometry with iodimetry, determine solubility of iodine, learn conditions and precautions in iodine titration, determine endpoint by various methods, and finally knows why iodine is standardized with sodium thiosulfate. Now this is a time to think and reflect. So take a pause and write down the answer for the question in your notebook. Why starch is added towards the end point of the titration and not in the beginning? So to find out this answer, we have to clarify some concepts regarding iodine titration, as iodine titration is a very important part of oxidation reduction type of titration, which is basically of two types, iodimetry and iodometry. Now, iodimetry, it is alternatively called as direct titration. So, here is a question, why iodimetry is called as direct titration? Because it refers to a standard solution of iodine. That means iodine is directly involved in the titration, whereas iodometry is called as indirect titration because iodine standard solution is not directly involved in this type of titration, but the liberated iodine during the reaction we have to estimate by using this type of titration, which is called as iodometry or indirect type of titration. As iodine titration involves participation of iodine, so solubility of iodine is the most important parameter, as everyone is knowing about iodine's solubility, as iodine is poorly soluble in water, whereas this iodine is readily soluble in aqueous iodide solutions such as potassium iodide or sodium iodide. Hence, the actual half cell reaction is as shown on the screen. The above reaction occurs at the end of the titration, but in iodometric type of titration, where excess of iodine is present in the form of triiodides, which is expressed the reaction which is shown on the screen. So the reactive species in iodometry is triiodide, and the reaction should be written as I3 minus, but for the sake of convenience we write it as I2, which is explained very well by the reactions which are showing on the screen. The E0 value of this system is plus 0.5345 volt. Hence, iodine is weaker oxidizing agent than the potassium permanganate, than the dichromate, than the ceric. Thus, there are several reducing agents which can be oxidized by the free iodine, which is having E0 value is less than 0.5345 volt. But there are also number of oxidizing agents which can be reduced by iodine ions, which is having E0 value more than 0.5345 volt. So, the most important sentence or very important sentence is So, iodine is opportunistic oxidizing agent, that is, it can act either as an oxidizing agent or as a reducing agent, which is depending on the conditions. For example, free iodine, like other halogens, can accept electrons and therefore it can be called as oxidizing agent. Whereas iodide ions can readily donate electrons, acting as an reducing agent. Hence, there is a double possibility of using redox properties of I2 or I minus, that is free iodine or iodide ions system in volumetric analysis for determination of reducing agent by oxidation with iodine and oxidizing agents by reduction with iodides. Now, in this iodine titration, there are some conditions which are very important for the conduction of iodine titration. As iodine is volatile in nature, the titration is conducted in the cold environment. This is also necessary because by the sensitivity of starch as indicator, which is diminishes with rise of temperature. If a starch solution turn blue by single drop of iodine, when this solution is heated, the blue color disappears. When it is cooled, the color is returns. Iodometry titration cannot be performed in strongly alkaline solution because iodine reacts with alkaline in accordance with this following equation. As iodine is interacted with strong alkali like sodium hydroxide, it gives sodium hypoiodide, sodium iodide, and water molecule. Then further this iodine is interacted with two molecules of hydroxyl group. It will forms hypoiodide and water molecule. The presence of this hypoiodide ion is inadmissible because it is a stronger oxidant than iodine and partially oxidizes thiosulfate to sulfate, which is which is very well explained by this equation or the reaction which you are showing on the screen. The higher the OH minus concentration in solution, the more thiosulfate is converted into the sulfate. Listen carefully, this is very important sentence. The higher the OH minus ions, that is hydroxyl group concentration in the solution, the more thiosulfate is converted into the sulfate. This side reaction makes exact calculation of the analytical result impossible. Care must therefore be taken that the solution pH does not exceed than 9. If the reaction results in the formation of H plus ions, they must be removed to ensure that the reaction proceeds to practical completion in the required direction. This is done by addition of sodium bicarbonate, which is reacted as the reaction which you are showing on this screen. The solution becomes slightly alkaline, that is, the pH is at 8, but this does not interfere with the titration. As the solubility of iodine in water is low, a considerable excess of potassium iodide must be used in iodometry for determination of oxidizing agent. The iodine liberated by the reaction then dissolves by forming the unstable complex salt. Formation of this compound does not interfere with titration of iodine with thiosulfate because the solution contains sufficient iodine owing to the reversible character of the above reaction. In case where H plus ions are consumed in the reaction, increases of solution acidity has a similar effect. When the reaction mixture is left to stand before the start of the titration, it is kept in a dark place because light accelerates the side reaction in which iodide ions are oxidized to iodine by atmospheric oxygen. Now, we have to take some precautions while performing iodine titration, and that precautions are as: the titration should not be prolonged unduly. Titration should be performed in cold solution in an Erlenmeyer's flask. The solution containing excess iodide and acid should not be allowed to stand for long period of time. If prolonged standing is inevitable, then the air inside the flask should be displaced by using sodium carbonate or dry ice before adding iodide. Whenever the solution needs to be standing, it should be done in dark than under direct sunlight. The solution containing iodide should be stored in umber colored glass bottle. Two important sources of error in iodine titrations are volatility of iodine and oxidation of iodide in acidic solution by atmospheric oxygen. In the presence of excess iodide, the volatility of iodine is decreased markedly due to the formation of triiodide ions. The atmospheric oxidation of iodide is negligible in neutral solutions in the absence of catalyst. The rate of oxidation increases with increase in pH in the presence of ions like copper and nitrites. The presence of sunlight will also increase the rate of oxidation reaction. Further, the oxidation of iodide ion may be induced by autocatalysis. Hence, above precautions need to be observed during the iodine titrations. Now, here is endpoint determination. And endpoint determination in iodine titration is done by using suitable indicator, and that suitable indicator is, or the ideal indicator for the iodine titration is, starch indicator. The advantage of this starch indicator is it is inexpensive, and the disadvantage of this starch indicator is it is insoluble in cold water, instability in suspension, formation of water insoluble complex with iodine. There is also drift endpoint observed in dilute solution. Starch contains two major components, amylose and amylopectin. This presence of amylose and amylopectin will affect on the endpoint coloration. How it is affects? Amylose, which is a straight chain, will gives blue color endpoint, whereas amylopectin will gives a reddish purple endpoint. With excess of iodine in the beginning of the titration, the indicator gives green color, but at the end it will gives an intense blue color, and the endpoint is very sharp. Sometimes instead of starch we can use carbon tetrachloride because intense coloration in presence of iodine, which is a favorable factor for carbon tetrachloride, which shows endpoint as reddish brown color to the colorless. Equally satisfactory results can be obtained by the chloroform. Now, preparation and standardization of iodine solution. A standard solution containing potassium iodide and iodate is quite stable and yields quantitative iodine when treated with acid. The potassium iodine, when interacted with strong acid, that is sulfuric acid, in presence of potassium iodide, it will forms potassium thiosulfate, with water molecule and iodine molecule. Standard solution can be prepared by weighing exact quantity of potassium iodide and dissolving in a solution containing slight excess of potassium iodide. By controlling the amount of iodate, an exact amount of iodine can be made available in the solution. The amount of iodine liberated is equivalent to the acid content of the solution. When a solution of acid, the normality of which has to be determined, is treated with slight excess of potassium iodide and potassium iodide solution, the amount of iodine liberated will be proportional to the amount of acid present. By titrating the liberated iodine with sodium thiosulfate, the strength of the acid can be calculated. It helps in two ways. First way is it forms a source of known quantity of iodine in titration, and second one is in determination of acid content of substance iodometrically or in standardization of solutions of strong acids. Now, standardization of iodine solution. This iodine solution can be standardized by using sodium thiosulfate solution or arsenic trioxide. Sodium thiosulfate in turns should be recently standardized by using potassium iodide or potassium dichromate and standard iodine solution. Reason for standardization of sodium thiosulfate. The reason is we are not sure of the water molecule present in sodium thiosulfate due to its efflorescent nature. It is unstable if prepared in ordinary distilled water and decomposes in presence of carbon dioxide to form sulfur. Moreover, decomposition is due to bacteria, and that bacteria is Thiobacillus thioparus. On long standing, which can be prevented by adding a drop of chloroform. The standardization with arsenic trioxide can be explained very well by using these reaction which you are showing on the screen. Now, standardization of sodium thiosulfate is done by three methods: by using potassium iodide, by using potassium dichromate, and by using standard solution of iodine. Now, here are the applications. The first application for iodometry titration is, example is assay of ascorbic acid by standardization by arsenic trioxide. Iodometry titration, example is assay of potassium permanganate, assay of potassium bromate, assay of copper sulfate, assay of chlorinated lime. Standardization by using sodium thiosulfate. So, this is all about which I know about this iodine titration, and this iodine titration hope you all are understood very well. So, thank you very much. We will meet very soon with another topic from pharmaceutical analysis. Thank you.